Phil King, and it's 8-bit Redux microcontroller hacking. There's a few things I just need to say up front. I apologize if my demeanor is a little strange. My laptop sucks in more ways than I can possibly relate, so I'm actually going to be working off the same screen you're looking at. If this seems a little odd, I apologize. But to give you an idea of what's going on, who am I? I'm Phil King, and specifically I'm a hardware engineer right now who does a lot of embedded systems development. Specifically, I'm working on IR wireless networking at a place called NetSchools. I've also been a game developer and a hardware enthusiast for at least 10 years now, and hopefully what you're going to get out of this is some of the fun that I've had with 8-bit system development. Who are you? To be getting anything particularly useful out of this, I sort of tried to develop a profile. You know the basics of electronics and electronic logic. This is why I ended up in the Uber Hexer track. Just a prerequisite that you are at least familiar with some of the basic terms. You know how to code, preferably in assembly language for reasons I'm going to get to in a little more detail later. You believe that 1K is actually useful space. It is surprising how much you can do in 1K. It's surprising how few people do it anymore. But as I'll get into the architecture of some specific examples, 1K is usually enough to do almost anything you want to do with an 8-bit embedded controller. Presumably you've built more software than hardware, which is hopefully why you're here to get something on my talk. And you know you could do this stuff if you could just get started. And that's what I'm primarily hoping to do, is direct you to get yourself set up with a small development environment, a lab, so you can play with this stuff. Basically, I'll cover what are microcontrollers, how to set up your lab, how to get some parts once you know what you want to be developing, some basic rules of thumb for building and debugging, an example project, which I will just give a cursory overview of, and the traditional inspirational message that has to go with every talk. Things I won't be covering. You will not see a lot of architectural specific details. Anything that comes off a data sheet you can look up yourself, and you don't need me reciting. There are literally thousands of different variations of microcontrollers, and what you specifically need is going to depend on your application. I also will avoid religious arguments, which are usually tightly coupled to data sheet details. I'm not going to tell you how to write code. Presumably you know that. I'm not going to tell you how to solder. I'm not going to tell you how to tell an ohm from an amp. If you aren't familiar with the terminology, don't give up, but I would encourage you to get some basic electronics texts and just find out, just learn the vocabulary. I won't tell you how to use no scope, and I won't tell you how to hack cell phones. Oh, sorry. Wrong. These are from a different talk. Okay. Thank you. Sorry about that. So what do you find in a microcontroller? The one thing that unifies them is, of course, a processor core. The original 8-bit microprocessors that we're all familiar with, the Z80, the 6502, and so on, were self-contained devices that had an address and data bus and basically were unified architecture processors that could do general purpose computing. Microcontrollers have taken those cores, or later variants of them, and embedded them on the same die with other resources. Specifically, what usually denotes a microcontroller is that you will have some onboard memory. And I note that it could be ROM, flash, EEPROM. Something that's interesting is that some of the devices that are one-time programmable, which is to say they can only be programmed once, are actually erasable devices. They just haven't put in a package that you can erase. Another thing you will find on microcontrollers is they generally don't have an address and data bus. They have programmable I/O ports, where you set port directions, you can twiddle the I/O pins, but all of the specific bus interactions are taking place inside the device. And then there's a library of peripherals that you'll find stuck on the most microcontrollers. The most common are UARTs, A to D, and D to A converters, so that you can do small, completely self-contained solutions. In fact, a lot of the smaller parts have an RC oscillator built into them, so that you don't even need to clock them externally. You can actually set a bit when you're programming it to clock itself, usually at some nominal slower rate, but it becomes a self-contained device where you literally just add power and it twiddles the IOs to do your bidding. And Why is this useful? You can create really cool, tiny little systems. It's really compelling when you have an 8-bit dip package that's doing something that you told it to do. It's nice to create cool software projects, but there's something particularly gratifying about hardware. Ubiquity. One of my favorite comments on this was in a 1976 small computing conference at MIT. They were talking about how computers were going to become ubiquitous, but of course there is a logical extension beyond which this will not go. For example, it's not like you need a microprocessor in every doorknob. If you've checked your door at the hotel here, there is in fact now a microprocessor in every doorknob. Low cost. Economies of scale are driving the cost of 8-bit microcontrollers into the floor, and it's great because you can buy individual parts for $1 to $2. Even the high-performance, high-end 8-bit microcontrollers are seldom more than 10, and in large quantities you will find that they replace random logic efficiently because some of the parts I've seen in super high production quantities are as low as 40 cents a piece. You get surprisingly high performance. CMOS can go really fast even if you're only shuffling 8 bits at a time. There's a company called Xenix, for example, that makes a 100 megahertz 8-bit microcontroller. And then simply scalability. There's a huge design space you get to play in. What do you not get? You don't get lots of memory. As I was saying, 1K of code space is a usable and fairly typical amount. This isn't to say you can't get a lot of memory. You can buy microcontrollers that have 128K of code space on them, but unless you're doing something that really needs to be moving, that really needs that large an image, you're probably missing part of the point. And so I encourage you to know your code. Beware of compiler assumptions, and then recursion versus the 2-deep stack. One of the nice things about playing with the microcontrollers is you get to know about what's going on at the meta level. In the AVR microcontroller, which is one that I'm using right now, the lower end versions have a separate, it's called a Harvard architecture, so you have a separate code and data space, and the two don't meet, and they've actually implemented the stack as a third separate hardware data space. It's only three elements deep. If you try to recurse with only a 3-deep stack, you're going to be in trouble. And then finally, like I said, you don't have typically a complex memory interface. A lot of microcontrollers have only a programmed I/O port. If you want to get something in and out of an external memory, you actually twiddle the address and data lines manually. There are some microcontrollers that let you assign some of the ports to be a memory interface, but even in that case, they make assumptions. For example, they own the memory. In even the old 6502, you had a memory ready indicator so that you could hold off memory accesses, which would allow you to have a DRAM subsystem or something that's slow. You could have a memory that you don't have complete control over. The microcontroller tends to make the assumption that it's the center of the universe. Okay, so you want to set up your lab. What are you going to need? What are you going to want? You're going to want a 128-channel logic analyzer, a 4-channel, 2 gigahertz oscope, a full system ICE, and universal device programmer. After you've laid out your $38,000, what do you really need? You need a digital multimeter. You can spend a lot of money on a digital multimeter. You don't have to. This is a Radio Shack special. It does 90% of everything you will ever need. It's normally, I think, like $22. I got it on sale for $16. It's accurate to 5%. It tells you what voltages are. I mean, all it does is extend your senses to be able to tell, are 2 points electrically connected together? Is there a voltage across 2 points? It does most of what you need out of a $100 fluke scope. A logic probe. A logic probe is just an LED on a stick that tells you the state of a pin. The reason it's useful is that you can stick an LED on a signal, figure out what the state of it is, but you're loading it. You can stick a driver in an LED on a signal and find out what the state of it is, but you can only tell as fast as you can see. Logic probes will generally be able to detect transient events. For example, if something is turning on for 1 millisecond every second, you're not going to see that. The logic probe will. And it's just a little chunk of logic hooked up to an LED. It's typically $15 for a cheap one. Again, you can spend a lot more, but I got a cheapo $15 logic probe that does pretty much everything I need. A microcontroller starter kit is what you're going to use to develop and test your code. And I've got an example of one here. Let me show you what the hardware looks like. Unfortunately, I did not take any pictures of this to get it set up on the slides, but it is a remarkably simple little board. You've got a couple of serial ports going into it. You've got some LEDs and buttons. You've got some headers, so you can plug it into the outside world if you want to. And then all you do is you download your code from your development environment. Which brings me to the development environment. I say a PC probably running Windows, even knowing that that will get me stoned with this audience. There are lots of good development tools that will run under Linux, and there's more coming every day, or will run under all sorts of alternate operating systems, the good ones. The truth is, though, that the manufacturers are selling to the commercial market, and the commercial market is still pushing the Windows development tools. So double boot your machine and bring up Windows every time you need to actually use their IDE, and then throw it away when you're done. Other useful stuff you'll probably want to have around. A breadboard. You can spend $20, and a breadboard is just a matrix of plug points that you can drop chips into, and it gives you a way of wiring things together quickly. A power supply. The great thing about this particular development board, and many of them, is that they are really forgiving on what you can put into them as power. They've got a regulator on here, so if you feed it anywhere from 6 to 15 volts, AC or DC, of any polarity, it's happy. It fixes it for you. An oscilloscope. I jokingly mentioned the 2 gigahertz 4-channel oscilloscope as something you want but don't need. An oscilloscope is a useful thing, and you can get them fairly cheaply, or you can build your own, which brings me to the home-built logic analyzer. A logic analyzer just lets you look at multiple channels. The only reason that's particularly useful is if you've got multiple data signals and you want to see what they're doing relative to one another, you need to be able to capture them all at the same time. There's a ton of debugging you can do by inferring, by just knowing what has to be going on, because that's the way you built it, but occasionally things don't work the way you built them. If you want to, and then, sorry, hold on. As an aside, I am used to doing this talk to a group of about 15 people at a time, and it's generally a much more interactive thing, which is why I'm sort of going off in all directions at once, and why I'm trying desperately to cling to my slides, because they are my touchstone with reality. The databooks you can get from manufacturers can be useful, but for the most part, they are out of date the day they roll off the press. The web is your friend, and application engineers are your friends. They will provide you the information you need to know, and I would encourage you to go ahead and call up the manufacturers and order printed copies of things like the instruction set, because you need to know this stuff. But for specifics about parts, pull down the datasheet, because you'll find out that datasheets often refer to the D, E, and F version of this part after they've fixed all the preliminary bugs. And then share and enjoy. You will find a vast amount of interesting, cool stuff about what people are doing online. So when you're trying to get your parts, the first thing to keep in mind, the manufacturer's job is to sell you parts. They can be very helpful, but call your thing, whatever you're building, a product. They build products. If you call up and say, hi, I'm building this thing, they will hand you off to a person who handles evolving accounts or developing accounts, which means you get shunted off into a backwater, and they don't really take you seriously. They won't take you seriously anyway, but you can mitigate that damage. Project realistic volumes, which is to say, don't tell them you're going to be producing 2.5 billion of your project, but I'm going to be doing 1 to 5,000 this year. That leaves open that, of course, the volumes will be ramping up. Engineering samples are a great thing. Generally, if you can, try not to talk to humans. My favorite example of this is the Maxim website. Allows you to get Maxim's integrated circuits, I believe up to 8 or 10 devices, completely off a forum on their website. You never have to talk to a person. You will talk to a lot of representatives. The manufacturers don't generally want to interact with the customers, whether they're design engineers or just people calling for general information. So they keep the layer of the representatives, the manufacturer's representatives, between you and them. They usually have pointers to these on their website, maintain a Rolodex. These guys' only job is to know your name and to try to get you what you need, as long as they believe that your product will be producing 2.5 billion units sometime in a few years. And then finally, know what you want. I point this out. It seemed obvious, but I thought I'd mention it because, as I said, there's a jillion different variations of every part. If you call up and say, hi, I want an Atmel AVR microcontroller, you've just narrowed it down to about 140 parts. If you say, I want an Atmel AT90-1200, you've narrowed it down to a family of about 10. But you have to specify everything. So if you don't specify something, they will often provide you parts which they pick at random from whatever they have on hand. Just be aware of how the part numbering scheme works and try to present complete information. And then finally, buy what you must. There's a lot of good sources for small quantity parts. DigiKey and JDR micro devices are two of my favorite. So once you've got your parts together, and you've put your lab together, and you've got your development board, and you're building, how are you actually going to wire whatever your prototype thing is? Breadboards are good, as I mentioned earlier, for wiring things up quickly, for doing small projects. Breadboards, as I said, are a matrix of interconnect where you're just plugging boards on this white bed of holes. They work for relatively slow things. If you are trying to do anything at 10 gigahertz, I'm sorry,